Today we're going to be working on a Mohr circle and the stress transformation and also shifting of the stress block. Now here on the right side we have the lecture notes, and on the left side we're going to be starting from scratch and taking the information to see how we would be solving it. So on the right side you'll see the problem, so we'll go ahead and draw it out. And if you have a piece of paper, feel free to join in and also mark it up yourself. Okay? So, and we've got it. Now, to make the explanation easier, there's only a compression on the x direction of the stress block. The y direction in this problem does not exist, so therefore it'd be 0. And one of the things that was asked was, well, why is it that shear, right, has arrows going this way, this way, this way, and this way? And so I wanted to kind of clarify that. Well, the question is, why does shear have really 4 different arrows, right? So let's start from the beginning. Let's try to understand that. Now, if we were to erase it so that we're focused on just 3, okay? If we say, talk from an equilibrium standpoint, right, is that if we have a shear here, we know that we have to meet equilibrium, therefore, by doing an equal and opposite. That's one. Once we do this, we'll do the check. Sum of the forces and the y. Does that equal 0? Yes, it does. Great. How about sum of the moments? Does that equal 0? No, it doesn't, right? Because you have a clockwise rotation. So therefore, you need to be able to counteract that with a counterclockwise rotation, which you'd be doing it this way and this way. And hence, you have equilibrium for shear. Okay? That's a pretty cool thing. So now, we've clarified that shear stuff, and we'll go back to this problem right here. Right? And we have a 12 KSI and a 6 KSI here. Right? And this is our problem. And what we'll do is, we will, down here, draw our, and we'll shift it over because I believe it's a little more like that, this problem, okay? And we're going to be asked to draw the Mohr circle. So we'll draw the Mohr circle first. And so when we do that, we want to label what we have. Well, we have sigma x, sigma y, and we have tau x, y. Those are our 3. So what is sigma x? Sigma x is equal to negative 12 KSI. Y, it is actually 0 in this case, right? And then we're looking at, let's see, okay, when we're looking at tau xy, which is 6 KSI, that's actually a negative, okay? Here, what we'll do is we'll say that that's x, could be our y, but really that becomes our sigma, and that becomes our tau, and we know that this is shown that way, okay? All right. So first what we'll do is we'll plot the 12 at a point right here. 12 KSI. Okay. And next, we'll be asked to draw the shear, okay? So I want you guys to look on this side right here. Now, this document right here is taken from the FE portion of the strength of materials. And in there, it says that for constructing Mohr circle only, shearing stresses are plotted above the normal stress axis, above, which is the top, okay, when a pair of shearing stresses acting on an opposite and parallel face of an element form a clockwise couple, okay? So what that means is that for the 12 KSI stress that we have, okay, this forms a clockwise couple, right? So if it flies clockwise, normal stress axis pair of shearing stress acting on opposite parallel face clockwise shearing stress are plotted. Okay, so that means that if it's clockwise, it is above. If it is counterclockwise, it is below. Okay, super confusing, right? But it's all in there. Okay, so we'll back up and we'll go and draw it right now. And so we'll draw the 6 KSI, maybe around here. That's 6 KSI. Right. So they're saying that clockwise is negative. Okay. And counterclockwise is positive. All right. So then we'll just kind of draw that dot right there. And that is representing the stress block that we have up here, down here. Make sense? Okay. So we've jotted 1 point. Now, if we had, I'm going to do it in gray. Let's just say we had a tension force that's associated with that. And then what that would do is I would plot it, tension, somewhere, like just for fun right there, right? And then right here, the direction is counterclockwise, yes? So that means it would be below that point. Does that make sense? So if you're doing like a different homework problem or something like that, then that's the other point that you would be drawing. So you essentially would have two lines to be drawing from your starting point to where you're going, okay? So I'm going to take that out now. We're going to focus on this problem. Boom, 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 boom. Okay. Now we've got that. We understand the direction orientation. Okay, we'll focus on the next portion of it. Okay, so now we're going to draw the rest of the circle. Okay. So to draw the rest of the circle, well, what we need to know is we need to know where the center is, and we also need to know what the radius is. Okay, so what is the center? Center is equal to sigma x plus sigma y over 2, and the radius is equal to sigma x minus sigma y divided by 2, parentheses, plus tau xy squared, square root. So this is literally plug and chug from the information that we have up there, information that we have up here, into here, and then we'll see that C is then equal to negative 6 KSI. And we'll have that the radius is equal to 8.49 KSI. Okay? So what I'll do is I'm going to try to clean this up now, right? I'm going to go ahead and, let's see, templates before. We'll do... Current template. I'm just going to add one. Okay, select. close. All right, we're gonna just copy this. Okay. Now what we're going to do is try to get all this stuff. And let's go ahead and resize it. So it's there. Let's take this. Let's go ahead and resize this. And there. All right. So we have our C, which is the center of our circle. Okay, great. So we said that the center of our circle is negative 6 KSI. Is negative 6 KSI, our center. Okay. And it's saying that our radius is 8.49 KSI, or 8.5, right? So if that's 6, 8.49 may be right there, right? We're saying that, oops. Is that point right there. Great. Now, what we're going to be doing is drawing the maximum principal stress and the minimum principal stress. So that all that means is take your radius and you'll add C and minus, you'll take your center and add your radius to 1, and then you'll subtract it, which will equate to 1 minimum principal and 1 maximum. So what we do is we'll take 2.49, which is taken from, if we take 6 KSI, which is negative, and add, so what we're saying is that sigma 1 is equal to C plus R. We're saying that sigma 2 is equal to C minus R. And that is equal to negative 6 plus 8.49. And right here we have negative 6 minus 8.49. Right? And that's equal to 2.49 KSI. And that's equal to negative 14.49 KSI. Does that make sense? Okay. So when we do that, we can start to draw our circle, right? Okay. So let's put those 2 points on the graph. We'll say that 2.49 is roughly around here. 2.49. Say that's sigma 1. And then we'll say that 14 sigma 2 is equal to negative 14.49. All right. So we draw our circle. Let's see if I could do it nicely. Boom. It's almost there. It's not bad. It's slightly off, but it's okay. So really what happens is that that's on the circle. So this location is our original problem where we had our box, right? And then we had a load here, load there, right? And I think it was going this, that point, okay, let's assign it a color. Let's see. Green. Green is good, right? Okay. I'm gonna try to do the same green right there. That's that point. Notice these points are always landing on the circle. I'm just not drawing it perfectly. So that's that point, right? All right, so what the Mohr circle allows us to do is that for an infinite amount of points, actually locate the combination between our shearing stresses and our sigma 1, sigma 2, or x stress and y stress. That's what it allows us to do now. Okay, and we've located our maximum principal stresses here and calculated that out. All right, so now we're going to be focused on plotting our tensile forces. Okay, so now what we do is we're going to take this. I make no money on this app. It's called GoodNotes. I've actually used it for several years, and it's always been pretty good. I've always kind of enjoyed using it, and feel like a lot of people benefit from it also. And I have no shares in the company. Alrighty. So as we've drawn here and put that together, now what we're doing is that we're going to be drawing a stress block. Now, I want you guys to kind of see what we're going to be doing. Now, one thing to note is that when we draw the stress block, right, the stress block is going to, for the maximum stress block, it happens when our when sigma 1 comma sigma 2 is maximum or minimum when tau is equal to 0. Okay, that's when we can actually plot, right? And also the rotation of that block is based on the original line or hypotenuse kind of line projection. Okay. Projection to the x-axis. Okay, so what that means is that if you take this hypotenuse and you were to project it onto the x-axis, that rotation is a counterclockwise rotation. And then in this case, it's counterclockwise. So what that allows us to do is that if we have a block, right? It's an ugly block, sorry. It's not perfect. That allows us to rotate it in that direction, which is counterclockwise. So that block will rotate in that direction. Okay? So one's rotation and then the theta, okay, is going to be half of what you get from the Mohr circle. So theta to half, right? So well, theta for the principal stresses P is equal to half of theta from the Mohr circle. Okay, and so right here, that theta that we get okay, which is then equal to 2 theta is equal to 10 negative 1 of 6 KSI divided by 6 KSI here. Let's see. Yep. Is equal to 45 degrees. Therefore, theta, P, principal, is equal to half of that, which is 22.5 degrees. Note that the opposite is going to be, which is going to be for the other theta, which is going to be for the shearing stress, would be off by a phase shift of, if we look at the circle right here, that's theta P. That's because it's principal. That's theta, I don't know if it's S or tau, but the idea is that one's angle here, or the other angle is there, right? So you actually solve for one, you actually solve for both. Okay. And so what that means is that, right, that theta there, or in that direction, is equal to 22.5 degrees. Now, the rest of it is going to be pretty simple, okay? Because what we do is we get the information and we know, okay, that we look at the principal stresses and we see that it goes to 14.49 degrees. Because if we look at here, we projected it onto here, right? So that 12 KSI, now pay attention, right? The 12 KSI now gets converted to 14.49. So if we look at the original problem here, it's saying that that compression force, 12, now becomes 14.49. People ask, well, how do I know which one goes to which axis, right? Which is the X, which is the Y? You go back to the original one right here. You see that it's 14. The original one was 12. And what does it become? It becomes 14. So we look at here, okay? We started off that point is 12 KSI. And it transforms to 14.49 KSI. That's golden. Okay, if you understand this, you're good to go. So that's 14.49. And then, do we have information in the y-axis? Well, we do, right? There we go. Positive means it goes out, and we have 2.49 KSI. Boom. We're done finding, drawing one stress block. Okay, great. So now what we're going to be focused on is we're going to draw the next one. Okay, so I'm going to do this thing. Resize. Go, maybe we'll do it right here. Something like right. Oops. Oh no. Come on, this thing is like so sensitive. There we go. Okay, so we did that, we put it there. Now, what we're going to be focusing on is to project it this way now. Oops. Okay. So maximum tau xy max is equal to 8.49 KSI. And that what that also means is that, see, when we look at this, it's really saying, well, if we have that center point right here and we were to project it up, I know this is a little off circle, but that is 8.49 KSI, right? That location is also saying that that's our center, our C, right? So that means that our stresses that we have is going to be whatever the center of our circle is for both axes. Okay, so what we know is this. Start with our we have our original block, right? The question is, which direction do we move it to, right? And we look at the original problem. This is our original stress block right there, right? Remember, that's the stuff. Now we're projecting it onto the other axis this way. So that is clockwise rotation. What that means is that our block rotates clockwise. Okay, so right, and then clockwise rotation, and it's also going to be 22.5 degrees because it's 45 degrees, which is equal, right? This just happens that it is 45 degrees, but if not, the thetas would actually be different. So we know that theta, oops, let's go with a thinner line. Theta is equal to 22.5 degrees. Great. So what does it also mean is that our shearing stresses, right, is also occurring, and we know that it goes this way, that way, this way, this way, and that's 8.4 KSI, 49 KSI. Okay, again, we have to look at how do we know that it was a downward arrow or not upward arrow, right, for the shear? Well, let's take a look. So if you look at the direction of the shear where it was before, it was right here before, and it went this direction. It did not cross into the other axes, right? It didn't go downwards, right? So what we know is that this value right here just increased slightly to this point, right? Increased slightly. So whatever that value that you had, you keep that same orientation, right? And we are increasing it to 8.49. So we have that. Now it also says that our center, right? See all that stuff? You take theta again. Now it's projecting onto this side. We've done that. I put a note here. When drawing the maximum shearing stress, the value is projected from the hypotenuse A. To the y-axis C. To the y-axis, right? This direction will match a stress block. In this case, it will need to rotate from A to C in a clockwise direction. Direction will in the opposite direction from the principal stresses, right? Because the principal stress was going this way. So once you actually do one of the stress block, you'll know how to do the other one, right? Because it just literally rotates the other way. So great. And then what that also means is that our 6 KSI, which is center of radius, is, and it's negative. So we say that all this here is 6 KSI. 6 KSI. Okay? And that is how we draw our maximum shear stress block transformation. And so, in summary, what we've done is this. And I'm going to close this out now. Original stress block. We've taken that information, drew the Mohr circle, okay? And then what we've done, we drew this point, okay? We found out what this point is, what this point is, right? And then we also found out what the radius was and the center. From that information, our principal stress is sigma 1, sigma 2, tau 0. And we have that it is counterclockwise rotation. The string stress means that it's rotated the other direction, right? And that's when we have sigma average, which is really the center of your circle, and tau max, right? And tau max, naturally, if you look at it, it's really saying what is your y-axis? Maximum, max, y-axis is what it's looking for. All right. Hopefully that clarifies and explains how to do the original stress block, Mohr circle, and the principal stresses and maximum shear stress plot.